Okay, I have here three problems I'm going to solve quickly without really showing or talking much through the work. I just want to show the thought process on paper so that you all can see the solutions to these problems, almost like you were looking at a key, except it's being worked out live. So I might give a little commentary, but mostly I'm just going to solve. Okay. So we have this block being pushed up a ramp, and if it's being pushed up, I'm going to draw it so that it's moving to the right. Weight pulls down, friction pulls back. I know there's friction because it gives me a kinetic friction coefficient. The normal force pushes up. And of course, there's a y component and an x component to weight. And the block's being pushed up. So the last of the four forces is the applied force, which I'll just call FA. And we're given the angle. Theta is, let's see, 39.5. We know the mass. And we know mu. Mu k. Whoops. Let me get that a little clearer. Okay. So the first thing to find, the only thing to find, is the applied force, FA. Now, to find that, we are going to need to use that F net. Oops, one last thing that we know. The acceleration. 3.2 meters per second, 3.25 meters per second squared. Okay. So to find the applied force, we're going to have to use that F net is equal to ma, and we could plug in with F net as the applied force minus Fk, because these two forces cancel out. Oops, also minus the Wx. So let's write in Wx, Wy. So let me start again. Fn cancels with Wy because the block is not accelerating off the ramp or into the ramp. No acceleration in this direction. So F net is simply going to be Fa is pulling up, Fk pulls down, and Wx pulls down. So Fa is ma plus the kinetic friction plus the x component of weight. We know m, we know a. The equation for Fk is mu times Fn, and Fn is equal to Wy. And of course Wy is mg times cosine where is it? Theta, the 39.5 degrees. And then we also have to add Wx, which is mg sine theta. So the applied force you can find by plugging in 65.5 times 3.25 plus 0.342. Again, we have another mass term, 65.5, 9.81. Gonna run out of room here. Cos 39.5. And then I need to also add another mg sine theta. So that'll be 65.5, 9.81, and sine 39.5. Okay. So you plug that into your calculator, and what do you get as your answer? And what you get when you plug in, I'm getting 791. And of course, the unit is newtons, because this is a force. Okay, there it is. That's the first problem. Okay, here's another problem. Block being pushed up ramp. Let me try that again. And whenever I have a block being pushed up a ramp, I draw my ramp so it's pointing, so it's going up as we move to the right. That way the block is moving in the positive or the rightward direction, tilted right direction. So let's draw the forces on the block. They're going to be pretty much the same as most scenarios. There's the normal force, there's weight, friction pulls it back because they say find the kinetic friction, the coefficient, and there's obviously an applied force if this thing is moving up the ramp. So weight has two components, the tilted x and tilted y component. So you draw those into your diagram, your force diagram. And we know a bunch of things. We know theta is 39.7. My 3's don't come out so good. 39.7. The mass is 55. And the applied force is 672. Alright, there's one last thing we know, which is really important. This block is moving at constant velocity. So whenever you see that, you immediately write down F net is 0. The same thing can be written, F net 0, if you see that the object is at rest. Okay? So that's crucial. That's a crucial piece of information. Here's how you solve. If the net force is 0, then the net x force is 0. We already knew the net y force is 0 because these two forces cancel out. The block isn't accelerating off the ramp, it's not accelerating into the ramp. So there's no acceleration in this direction, so we ignore those. We can almost just ignore those forces altogether. So the only forces we really have to deal with are the x forces, and that net force is 0. So what's the net x force? It's Fa minus the leftward forces, so minus Fk minus Wx. So you write exactly that. Applied force minus kinetic friction minus the weight down the ramp, or the x component, tilted x. When you add up all the x forces and subtract the negative ones, they make 0. Okay. So let's plug in. We're trying to find the kinetic friction. We're trying to find mu k. We already know Fa, so there's nothing to, no way. We're just going to plug in this value for Fa. So Fk we don't know. We have to break that into another equation. We know that the kinetic friction is mu times the normal force, or in this case, the normal force equals Wy. So Fk is mu times Wy, and Wy is mg cos theta. Wx, we have to plug in an equation for that. So Wx is mg sine theta, and this is all 0. So if you add mu k mg, if you add this term to both sides, you get Fa minus mg sine theta is mu times mg cos theta. So we isolated the term. We've isolated the term which contained our unknown mu. Now you isolate that factor, so get rid of these factors. You divide both sides by mg cos theta, and this is going to be, this is going to be kind of a tricky thing to plug into the calculator because there's going to have to be a lot of parentheses to get this into our calculator correctly in just one line. So mu k, you see that m cancels here, g cancels, cos theta cancels. So we've isolated our unknown mu. It's Fa, which is 672. Put parentheses around this. Minus 55 times 9.81. Times the sine of theta. 39.7. I'm doing this with my finger. I don't have my stylus with me. And you divide all of that by M55 times G times cos theta, 39.7. And you solve for mu k, plugging this all into your calculator. Right, I've used dots here for multiplied. These are all being multiplied. This is messy, but you plug it in, and here's what you get as your answer. Now I'm plugging this into Excel to do the calculation, so hopefully I've done it right. But there's a lot of text, and I very well could have messed up. So you get as your answer something, hopefully, you get 0.79. That's mu when you plug this big mess in. And remember, if you're doing this on a TI calculator, make sure you put parentheses around the entire denominator if you're using multiplies here and here. And that's your answer. Here's the last problem. We have a block sliding down. Now, I always want my block moving to the right, in the tilted right direction. So that means I want to draw my block like this. So that, I want to draw the ramp like that, so the block is moving to the right. So there's the block. It's not levitating, that's just my poor drawing. And there are forces on the block, of course. There's always weight. There's the normal force in all of these problems. The question next is this. Is there any friction acting on the block? Well, the block would be sliding down this way, okay? So if there were friction, friction would be acting up the ramp. But it says frictionless, so there's no friction. So in fact, these are the only two forces acting on the block. Now we know that weight has a tilted y and a tilted x component. Wx, wy, that's the angle there. Let's write the givens. Theta is 19.6. 19.6. Okay, let's try one more time. We also know the normal force on the block. Oh my gosh. This is no good. The normal force, Fn, is 723 newtons. And that's all we're given, and we have to find the acceleration. Well, the acceleration will be found using F net equals ma. There's really no other way to find acceleration, so we know that's the equation to start with. You start plugging in, okay? Now, F net in the y direction is 0 because there's no net y force. The way we know that is the block isn't accelerating off the ramp. Clearly that's impossible. And it's not sinking into the ramp. We're not told that. So therefore, F net y is 0, and we can just plug in F net x for F net. We can just ignore the y direction and focus only on the x, because the y cancels out completely. So plug in Wx equals ma. Alright, we're getting closer. If we can plug in mass, and if we can plug in Wx, we could solve for acceleration. So let's do this. Let's plug in for Wx and see what happens. Wx, we know, is going to be mg sine theta. Right? And the first thing that we see is that the mass cancels out. So in fact, if you want to solve this problem, this is really, really easy. The acceleration, if there's no friction, the mass is inconsequential. The acceleration is just g sine theta. Wow, that is super easy. So the normal force that's given here, this is extra information. We don't need it. It's not used. The only given that actually matters is theta, because we know this is 9.81, that's 19.6. So plugging in, what do we get? We get 3.29 meters per second squared. That's our answer. And that's a super easy problem. Now, here's the thing. If I gave you a frictional force, or if I gave you a coefficient of friction, then this would not be such an easy problem. If there were friction, then we couldn't ignore mass, and in fact, the mass would in part determine what the friction force was. Because the greater the mass, the greater the normal force, and then the greater the friction. So this is only going to be such a simple problem if it's a frictionless ramp. That's the only scenario where the mass cancels out like this. But that's nice. This is a fun, easy problem. And we can see that by plugging in some of the givens, plugging in the equations and seeing what happens, simplifying. Okay, so there it is.